to start the session.
Okay, so welcome folks. I appreciate everybody taking the time to prepare the presentations and to share it with colleagues. It is a challenging time, but science moves ahead, and if anything, science is more necessary than ever. Our first presentation today comes to us from Drake University. The title is High-Harmonic Generation in the Water Window from Mid-IR Laser Sources, and I believe the presenter is Keegan Finger. Keegan?
Yes, thank you. Get that pulled up here. All right. Hello, my name is Keegan Finger from Drake University. Today I'll be presenting my research on high harmonic generation in the water window from mid-infrared laser sources. So let's jump right in. As a brief overview of what I'll be talking about today. First, what is the water window so that everyone knows what we're talking about here. Second, what is high harmonic generation and a little bit of the process of how it works. And then the method that we're using, namely the R matrix with time dependence method. And then finally, we'll end with some results and some concluding remarks. So first off, what is the water window? Well, the water window is a region of the electromagnetic spectrum in which water is transparent to soft X-rays, or at least partially transparent. And this extends from approximately the K absorption edge of carbon at 282 eV to the K edge of oxygen at 533 eV. And it's in this region that these proteins and lipids are more opaque than water, so it allows us to more easily image these materials in their aqueous environments. And what we're trying to look at here is how do we generate light sources in this region efficiently. And one such way is high harmonic generation, which is a nonlinear process. So in this model here, this picture is from Midikora from National Photo, but the idea was introduced by Paul Corkum in his 1993 paper, where he suggested a three-step model where first an electron is tunnel ionized or over the barrier ionized away from the nucleus, which we can see in step A here, at which point the electron is then accelerated away from the nucleus. And then as the sign of the laser field or of the electric field generated by the laser changes, the electron begins to accelerate back towards the nucleus, where it recombines and emits a harmonic spectrum. And it's this process that allows us to generate high harmonics of the order of 500 or 1,000. So we get very high harmonics, hence the term high harmonic generation. So the highest photon energy given by high harmonic generation is given through this formula, where IP is the ionization potential and UP is the ponderer motive energy of the electrons in this region. And our ponderer motive energy can be found using this equation. So if we break down this equation, we can see that it depends on the laser peak intensity. We're using a 6 cycle laser pulse, but this is the peak intensity of that pulse, as well as the laser carrier frequency. And as I'm sure you're all aware, we can easily find the wavelength from that, from the frequency, as the wavelength is what we are actually varying in our R matrix method. So then the question that we're seeking to answer throughout the course of this research is, can we generate water window harmonics purely by increasing the intensity and wavelength as this formula suggests? And we're going about this by using what's called the R matrix with time dependence method, or RMT. So the goal of this method is to solve the time-dependent Schrodinger equation. And we do this using a time-dependent wave function from which we find our harmonic spectrum. Granted, there are some steps in between here, but that's the gist of it. But why use RMT? Well, first, RMT includes some multi-electron effects that aren't normally taken into account when high harmonic generation calculations are performed. And it has been shown that these multi-electron effects do influence the harmonic spectrum, but we're not entirely sure the extent of these multi-electron effects. Also, RMT was developed with high-performance computing in mind. So this allows us to have much higher runtimes without having to worry too much about the computational complexity. So we can run larger and larger jobs without worrying too much about the overhead. Speaking of high performance computing, we're running most of these jobs on the Frontera supercomputer out of the University of Texas. Frontera is currently the 8th fastest supercomputer in the world at a whopping 38.7 petaflops at maximum capacity. Even with this speed, our calculations take anywhere from 5 to 10 hours with an allocated 1,000 to 1,300 cores per job. So we're using a very significant amount of computing power for one calculation. So the R matrix with time dependence method uses a small complex inner region that includes multi-electron effects. And then as the electron exits this inner region, we have a larger, easier to treat outer region, which treats the system as a single electron reacting with a charged core. This helps us to have a much larger outer region without worrying too much about the computational complexity. Furthermore, the computational methods are optimized for each region, such that in the inner region, we're using a B-spline basis to ensure that we have the accuracy required to include these multi-electron effects. And then in the outer region, we're using a finite difference grid to allow us to have that expansive outer region. And then at the boundary between the two regions, we impose a boundary condition such that the value from the inner region at that boundary has to be the exact same as the outer region at that boundary. So then some results that we found so far. This is our first preliminary result that we found, just as an example of a high harmonic spectrum. And all of the results that we'll be looking at here are for neon. So this one is for 2000 nanometer pulse at 5 times 10 to the 13 watts per centimeter squared peak intensity. So if we break this down, we can see our fundamental peak right here. And then our plateau, this is the main region of interest. This is our the high harmonics that are generated by our high harmonic generation. Then we have our cutoff, which we saw the equation for just a couple slides ago. And then finally, the rest of this is just noise. So the first thing that we did is we started increasing the intensity, starting with 5 times 10 to the 13 watts per centimeter squared, and then up to 8 times 10 to the 13, and 1 times 10 to the 14. And again, this is for the peak intensity of a 6-cycle laser pulse. And as we can see, or as you see here, we see approximately a linear increase in the cutoff from increasing the intensity, which is exactly what we would be led to expect from the equation for the cutoff that we saw previously. You'll also notice an increase in intensity on our vertical axis, which is also to be expected as we increase the intensity of the laser pulse. You will notice that the intensity of these high harmonics are significantly lower than the intensity of the laser pulse, and that's because high harmonic generation is overall a very inefficient process in regards to intensity. From here, the next thing that we did is we started increasing the wavelength, starting with 1 times 10 to the 14 centimeters squared at 1400 nanometers. And we increased that to 1600 nanometers, 1800 nanometers, and 2000 nanometers. And this is where we were at the end of the previous slide. And we can see approximately a quadratic increase in our cutoff when we increase these wavelengths. And we've pushed this as far as 2200 nanometers so far in this process. We're expecting approximately 2800 nanometers to be required at this intensity to get us into the water window, which starts at approximately 282 EV. So as you can see, we're still a little ways away, but not as far off as we were. So then some of the conclusions that we've been able to draw so far. First, changing intensity and wavelength does result in the expected changes in the harmonic cutoff, which is fantastic to hear and kind of shows us that the method is doing what we would expect it to. Next, our current laser parameters result in cutoffs close to, but still below the water window. I touched on this previously. We're expecting approximately a 2800 nanometer pulse required for imaging in the water window. So we're not too far off. We're only about 600 nanometers off, slowly increasing that as we go. And hopefully we'll be able to get some results in the water window soon. Further work does need to be done to improve the efficiency of these calculations. As I mentioned, we're looking at 1,000 to 1,300 cores for 5 to 10 hours. And some of that time is spent for the cores waiting for other cores to finish, since there is a bit of interplay there. So we can speed up the calculations a little bit by working on our allocations. And then lastly, we plan to determine the influence of multi-electron effects on the high harmonic spectrum using a single active electron code and comparing these results to our current code, as we know that multi-electron effects do play a role in high harmonic generation, but we're not entirely sure what the extent of those effects are. And with that, I'd like to acknowledge the NSF for their support, as well as my advisors for advising me. Are there any questions?
Great. Thank you very much, Keegan. There's time for 2 minutes for questions. I'm going to monitor the chat if anybody would like to post a question, or if somebody would just like to come in and ask a question. Be happy to field that. I'm sure Keegan would be happy. So Keegan, while some people are perhaps coming up with questions, I want to know, is there any way of extending the cutoff other than, the ionization potential and the wavelength of the driving field?
Not to my knowledge. If we go back to that equation here through all these slides. So, unless you want to start messing with some fundamental constants, but I feel like that's probably not the best idea. To the best of my knowledge, the only way to increase the cutoff is through ionization potential and the Poynter motive energy.
Okay. Is there any possibility of doing harmonic generation off the harmonics, like second harmonic generation of a harmonic?
That's actually kind of what's happening. Is the electrons, when they recombine, can somewhat bounce other electrons out or bounce themselves back out, and then recombine again, which is how we get the really high harmonics. But as far as generating harmonics from the harmonics, I'm not entirely sure.
Okay. If there are no other questions, we should probably move on. Congratulations on a great call to kick off this session. Thank you.